Hello everyone, my name is Tara Murphy and I'm a fourth year theoretical physics student at Trinity College Dublin. And today I'm going to talk to you about my current project at Tyndall Institute, applying inverse design to nanophotonics. So we begin with Moore's law. Moore's law is on the verge of, no longer being a law. From the 1950s up until now, we have scaled our devices from meters in length to mere nanometers. But because of fabrication constraints and quantum mechanical effects, we are moving into a different age of technology where photons or particles of light replace our everyday electronic current. However, doing this, it's almost like we're going back in time, where computers occupied whole rooms. Look at Google's IBM, for instance. We need to scale down our photonic devices as well as satisfy a variety of requirements as shown, such as minimizing the loss of photons. But how? When designing a device, we also need to keep in mind the space of designs possible is incredibly large due to the number of parameters such as length or electric permittivity of the device subject to change, and it can be computationally very expensive sometimes, but this is where inverse design comes in. Inverse design is a computational technique which focuses on a function commonly known as the objective function, and it describes the performance of a device. So instead of simulating each individual device, we have a different problem. We must try and minimize the objective function with respect to certain parameters and given certain constraints, S in this case. So let's go through this and see it in action. Here I'm going to take an example from a group at Stanford. We are given a 90-degree bend waveguide, and we must discover which design can maximize the transmission of photons from A to B. Our parameters in this case would be the electric permittivity inside the device. In this case, the objective function can be described by something called a modal overlap, which describes the amount of photons reaching point B. And our job is to find the gradient of the objective function with respect to the electric permittivity at each point. So let's look at one element of the gradient, and we can rewrite it as a product. The first derivative can be solved analytically, but the second derivative can be a bit tricky. But we must remember that light must obey Maxwell's equations, which can be rewritten in this certain form. We can then manipulate Maxwell's equations, and setting the sources to be constant in time, we obtain the following equation for the second derivative. So substituting this into our initial equation, we obtain this formula. This is commonly known as the adjoint equation, and it can be solved numerically. So using this method, we can easily solve the gradient of the objective function with respect to certain parameters and use this to explore the space of devices which will maximize the transmission. So back to our problem, the waveguide. By calculating the gradient and tweaking the parameters through each iteration, one can see that the transmission of photons increases dramatically. So inverse design reduces the computational expense while discovering unintuitive designs for devices with it. And really, this is the beginning for inverse design in nanophotonics. Who knows what devices we'll create next? Thank you so much for listening, and I hope you enjoyed my talk.